Hi everybody, today's lesson is about LCR circuits and resonance. So what does the word resonance mean? We've come across this word in mechanics when we were doing simple harmonic motion, and resonance was when the natural frequency matched the frequency of the driver, and something will oscillate with very large amplitudes. We've also come across the word resonance when we did standing waves in strings and pipes, and that is when the wavelength of the incident and the reflected waves are the same when they superpose, and so you have very loud sounds. So, coming on to electricity, what is resonance? Resonance occurs when the current in an LCR circuit, or a circuit which contains an inductor, a capacitor, and a resistor, is a maximum. So for the current to be a maximum, we want the impedance to be a minimum. And why do you want that to happen? Because your circuit current is related to the supply voltage and the impedance. So if your supply voltage is the same, then if your impedance becomes very low, then your current is going to become very high. So how can we achieve this? Now, AC circuits have got what we call frequency, and it's possible to either change the frequency, or it's possible to change, if you have a variable capacitor or inductor, to change the capacitance and inductance. So how does it all make sense? So let's take this one at a time. So if you're looking at the voltage across the resistor, V is equal to I times R, and R is a constant, it's not dependent on frequency. However, the voltage across the capacitor is IXC. Now the thing is, XC is equal to 1 over 2 pi FC. That means your reactance of the capacitor is inversely proportional to the frequency. So if the frequency increases, then your reactance is going to decrease, and that's going to have an effect on the voltage across the capacitor as well as the current. Okay, and then you also have the voltage across the inductor, which is IXL, and your XL, which is the reactance of the inductor, is directly proportional to the frequency because it's equal to 2 pi FL. So frequency has an effect on the reactance of the capacitor as well as that of the inductor. Okay, and so that's going to have an effect on the overall impedance of the circuit. So let's start by drawing an impedance phasor diagram for resonance. So now what's that going to look like? Now, as always, the resistance is unaffected by frequency, and it's customary to draw the voltage, the resistor, resistance of the resistor as the horizontal vector. Now, the reactance of the capacitor is 90 degrees behind the resistance, and the reactance of the inductor is 90 degrees ahead of the resistance. So if you look at the reactance of the inductor and the reactance of the capacitor, they are 180 degrees opposite each other, and they have a cancelling effect. Now, and the circuit current depends on the vectorial addition of these three. But if XL equals XC, then what happens is that your impedance becomes equal to resistance, and that is the only thing that's going to impede the circuit current. And so your Vs becomes equal to VR, which is I times R, and you're going to get a big current. Now, if you also look at the voltage phasor diagram, so if I draw a voltage phasor diagram here, at resonance, what actually happens is that the voltage across the resistor does not change. That's the only thing that stays the same. However, the voltage across the capacitor will be equal and opposite to the voltage across the inductor, And so they're going to again cancel each other, and that's how the voltage across the resistor becomes equal to the supply voltage, and that's equal to I times R. Okay, so so the thing is, if you have a circuit with a variable frequency, and you will notice, and if you draw a graph of the size of the circuit current against different frequencies. So frequency is measured in hertz and current is measured in amps. When it is not at resonance, that means when there's a difference between XC and XL or VC and VL, okay, you're going to get small frequencies. But as you keep changing the frequency, as it approaches resonance, the current is going to get very big, and increasing the frequency any further, the current is going to drop down again. Okay, so this peak here, when the frequency, whatever frequency for which the current is a maximum, is called the resonant frequency. So that kind of concludes this thing about resonance, but you might wonder, why are we learning about this? Why do we use it? Now, this is used in radio tuning. You know, when you turn the knob, what you're actually doing is probably having a capacitor at the back which has interlocking plates, and you can change the area of overlap of the plates and have an effect on the capacitance, and that's going to change the reactance of the capacitor. You can also have variable inductors again, and changing the inductance will have an effect on the reactance of the inductor, and therefore will have an effect on the impedance. So bye for now.